No, you just seem like your usual asshole self.
Oh, that was.
I can only aspire to reach your level. I don't think it's going to happen. I'm going to need some help. I don't know. It's like Super Saiyan asshole. I can't do it. My hair won't go gold.
Got a smile on now.
Yeah, no, I did before too. That's why I was able to handle it. Yesterday, I don't think I would have been able to handle it. All right, guys. So, any questions? I got one question I didn't get to yesterday. I want to do first thing.
And then are we going to talk about secants and code whatevers?
Well, yeah. I figure the next topic we probably should cover.
Oh, as long as you.
Which section?
84.
Oh, there it is. There it is. So, in this section, we didn't cover this yesterday either, but the idea is kind of nice. You can define speed. If I have somebody rotating, so I had a really cool problem way back in one of my physics classes, but it's based in trigonometry. You have a bug that's crawling out from the middle of a record player. Remember records? Yeah. The bug couldn't really do it on a CD very easily. And it's talking about how its speed, angular speed, if it remains constant as it's crawling out and all that kind of stuff. So angular speed would be the degrees that you go through over a certain amount of time. So think about that. If I'm driving around in a circle, I've got a certain linear speed, because if I push on the accelerator, I go a little faster. But I also, and I can see the speedometer changing. That's just measuring how the length that I'm traveling. But I'm also going through a certain angle over a certain amount of time. So that's angular. Any angular kind of motion normally is given these nifty little symbols. Angular speed is given the symbol like that. Omega equals theta over time. So this is just like velocity equals distance over time. So if I go in a circle, I've gone through a certain number of degrees or radians in how much time. If I divide those two, that's my angular speed. Just like if I want to know linear speed, how far did I go divided by how long did it take me? That's speed. You with me? All right, good. So the weird thing is, if I have my bug crawling out, if he's crawling straight out and this thing is rotating, it's of course maintaining the same angular speed. It's just whatever the speed of the record is. So it's not so a bug sitting out here and a bug sitting there on a record player, they're going to have the exact same angular speed. Because they're going to go through the same angle as each other over the same amount of time. So it doesn't care about how far you actually go. It just cares about how much of a degrees do you go through, or radians. And then, of course, let's put this here. Angular speed. Linear speed is velocity equals distance over time. And in physics and stuff, they use the letter S. We used the letter S yesterday for what? Arc length. Cool. So if degrees is purely, degrees itself is made up, but the angles are measured with radians or degrees. If I want to know how far I actually went, I got to look at the arc length. So here's the connection between these two. What is arc length? You remember arc length given a certain radius circle? If I go through a certain angle,
Radius times theta.
yeah, S is r theta. So what's the connection between angular speed and velocity? What would I do to this to make it become this? How do you make theta become S?
Plug theta.
You multiply it by R. So then V is R omega. You call it W. I don't care. You don't have to do it as Greek letters. You just call it curvy little W. All right? Whatever you want to call it. I don't care. Do you see? And if we try it, is this true? R times theta over time. Well, what's R times theta?
R theta.
S.
R theta, which is
S.
S, which is linear speed. So if you know, it kind of makes sense, because if the bug crawls outward, he's going the same angular speed, but the further he goes out, the further he travels, right? So his linear speed is increasing as he's going out. Let me say it again. You ever play on those merry-go-round things when you were a little kid?
Yes.
You know? Then your big brother or something would come over and just, stop it! Right? That was me. Or my big sister did it to us when we were really little. Yeah. So you'd rather be closer to the middle. Actually, on the outside is going damn fast, but the angular speed is exactly the same. What changes as you go out, of course, is your radius. So it kind of makes sense that the connection between linear speed and angular would be multiplied by the radius to see how truly far you're going, how truly fast you're going. Maybe. All right. So this problem says I've got a truck with a 48-inch diameter wheels. So the wheels, 48 inches. It's traveling at 50 miles an hour. So the linear speed is 50 miles an hour. Find the angular speed in radians per minute. And then how many revolutions per minute do the wheels make? Okay. So one evil little thing is this is 50 miles per hour. And so they just made this problem, what do you call it? Conversion hater's nightmare. I got 50 miles per hour. I got a 40-inch diameter wheel. I've got, they're asking me per minute. You see all the conversions that have to happen here? Maybe so?
Yes.
Okay. So it all depends on which way. I'd rather not change inches into miles. Right? Because that would be point, something. So I'd rather change miles into inches so that these actually hook up.
Why wouldn't you change it to feet?
Oh yeah, you can make a meet in the middle.
Yeah.
Sure. So 48 inches is how many feet?
4 feet.
Yeah, it's 4 feet. And then how do you change miles to feet?
It's like multiple 5,000.
5,200.
Yeah, 5280 feet in a mile. You didn't know? So you just multiply those. 26,400? 26. No, maybe not. Maybe it's 260. I got my comma in the right place. 100 turns out to be that.
Yeah, 264,000.
Alright. So now we've got things in our problem matching in units. It's a good idea. So this is 4 feet in diameter, which means the radius is 2 feet. And I'm traveling at a velocity of 264,000 feet per hour. How do I make that per minute?
60.
Yeah, so it would say that one more time. 60. Do what with 60?
Alright.
Cool. All right. So help me out with that. That's
4,400.
4,400? Cool. 4,400 feet per minute. So the next time you're going down the highway at 50 miles an hour, probably not of your choosing, but you're actually going 4,400 feet per minute, in case you were curious. Right? You say that to somebody and they'll go, whatever, man, just get us there. Okay, so let's see what's happening. So that's the first step of this problem, is to get all the units to kind of match up. Now, the first question is, what's the angular speed, right? So write down the formula for angular speed. So the angular speed is, and actually let me do this. What did we just figure out earlier? Velocity, linear speed is what?
S over T.
True, but related to omega. R omega, cool. So that's a relatively new equation for us. So they're asking me for omega, and I know V, and I know R. Right? Just plug and chug. But the problem with this problem was, you got to realize you got to get all the units that are going to match up, or else they're never going to cancel appropriately. So what do you plug in?
R.
4,400 equals
Yeah, 4,400.
2W.
Yeah, the radius is 2 feet. Oh my,
Yeah, sorry, Omega.
it's all good. And now watch what's happening here, though. Let's go ahead and write this down. So this is 4,400 feet per minute, and this is 2 feet times omega. Now what happens when you divide by 2 feet? This is
They
interesting.
cancel.
Yeah, omega equals 2,200
Minutes.
per minute. And I said this yesterday, but it's a really easy thing to not realize. Radians kind of get out of the way of what's happening. Because this is like radians per second times feet. And the answer is not foot radians per second, right? You know what I'm saying? I'm going about 80 foot miles per hour. I'll be, mile radians, what the hell would it be? So, this is actually radians. Radians are the true measurement of motion, right? So but they're all based on the unit circle. That's why they kind of get out of the way of any other unit that I want to bring in. So they're there, but they just immediately get out the way when I convert it to linear stuff. All right. So that's number one. I'm going 2,200. My wheels are going 2,200 radians per minute. Freakiness. And that's what they wanted for part one. Now, how in the world do I go to part two? Revolutions. Yes, sir.
I did it completely differently.
Okay.
I did it, I figured out the revolutions first, and then I plugged in the radians. Here, I'll show you. This is how I did it.
So you did part B first.
What I did was I said, how many rotations is there per? I don't remember what the hell I did. I did something, and it worked.
So you worked with the circumference.
Yeah, I made it circumference, and I figured out how many is one rotation, how far does that get me, and then I converted that to like 3 pi feet. I'm canceling out my feet. And then, so it was like 5,280 feet is a mile, over 1 mile. And then 1 rotation over 3 pi, which was
So what answer did you get?
the right answer.
Okay.
It was 1320 over pi, and then all I had to do to change it out was, like you said, cancel out the radians, which means put the pi up there for radians, and then it cancels,
Okay. Sure.
and it works.
Good. That's fine. Yeah. So very often I would do part B before part A in like a physics class or something. Right? I mean, that's just a different way to kind of look at the problem. So one way to look at, I'm not even going down the road, because that's fine, that'll work. But how do I go from where I am now to revolutions? It's not as hard as you think. How many radians are in a full revolution? 2 pi. So if I went 4 pi radians, how many revolutions is that? 2. What'd you do? You divided that by 2 pi.
That's what I did. I put 2 pi up where it was rotation,
There you go.
because I figured a rotation is 2 pi.
So if I got 2,200 radians per minute, how many revolutions is that? Well, I just put rad down there so it cancels, right? I just look at it as a straight up conversion. Revolutions, there's always going to be 2 pi radians in 1 revolution. We know that. We're just not used to saying the word revolution in this way. But 1 revolution is a complete turn. That would be 2 pi radians. They are the same thing.
Thank you.
Use your words. So then, what's 2,200 divided by 2 pi? Oh, yeah. Well, 1,100 over pi. All right.
Yeah.
And then, then you can do that whatever the hell that is. You can divide that out. Because now we're going to tell somebody revolutions per minute. That doesn't make any sense to me as a human, right? 100 over pi revolutions per minute. So whatever that is on your calculator, bam. Cool. All right. I don't want to take the time right now to show, because you could take the circumference of this, which would represent a revolution. And so if I'm going 50 mile an hour, I change that into feet. I get my circumference in feet. I divide those. It tells me how many revolutions per.
It was a shorter problem.
Fine. Right.
I'm not
Okay.
Shorter is better.
Ryan wants to see how much patience I have today.
Do you have a lot?
Not anymore.
Did I ruin that this morning?
Yeah. Has everybody got that before I start? Sure. This is older stuff, so I figured it would be safe.
Go.
48 in the same section? Oh, good. All right, perfect. Somebody asked me about this morning. I was like, this is one I definitely expect a question on. So be really careful about what they're asking here. They're just asking you to find a coterminal angle that's between 0 and 2 pi. So let me do a couple of side notes here real quick before we get into this. And the first good question real quick is, what units are on that thing already? It's definitely radians. Why do I know it's not degrees? Because there's no degree symbol. So it doesn't have to have a pi in it. And in fact, I could have pi degrees. If I put a degree symbol on it, it's degrees. If I don't, I have to assume it's radians. Period. Radians are real numbers. So I could certainly go 10 feet around a circle. That would be 10 radians of motion. Not 10 feet, but if I move 10 radians around a circle, that would be 10 radians. So real quick, two easier problems. If I said 3 pi, why is that not good?
It's not inside 2 pi.
It's not between 0 and 2 pi. How can I force it? I don't want to change the angle. Where would 3 pi be?
First
Yeah, it'd be a whole rotation and then this much. Here's 3 pi. So just to get it to go in there, I just make a coterminal angle that's not got that extra revolution. So what do I do to this? I just subtract
2 pi.
a revolution. So now that would be in there. It's the same exact angle, right? It's a coterminal angle. It's the same angle. Just took out the extra revolution. So people freak out about this problem for a couple reasons. First is it's like, what units is that? There's no pi in it. Is it radians? Yes, it's radians. There's no degree symbol. Is it more than 2 revolutions?
No.
I mean, not 2 revolutions. More than 1 revolution?
Yes.
Yes. Because 1 revolution would be how much as a decimal?
Oh.
1 revolution would be 2 pi radians, which is roughly 6. It's beautiful. Love it. Very roughly 6. This is obviously more than 1. So what do? You do exactly what we did here. Subtract off a revolution. And you stop. Why not? There's nothing wrong with that. That's the exact answer, so I can't possibly say anything against that. You can get a decimal representation, approximation if you want to, but didn't ask for that, so what the hell. The main thing there is just realize it's radians, and it's got an extra revolution. You just subtract that bad boy out, and you are done. Exactly the same thing we did here, right? I really want you guys to realize this problem everybody seemed to get. It's the exact same damn problem. Because what is 3 times pi?
9 something.
9 points, almost 10. So it's almost exactly the same damn problem. Almost exactly the same damn problem. Okay? Yeah.
Number 70.
Oh, so this is kind of like that one we just did, but a little bit more targeted. Right? That number 84 had 1 million steps to it. Number 70 just has how many revolutions? So the car wheel of 30-inch diameter. How many revolutions will it go as the car travels a distance of 1 mile? All right, so there's a little more interesting stuff to it. So, of course, the first thing I can do, before I even worry about what math I'm going to do, yeah, so the radius here would be 15 inches. And what would that be in feet?
1.25
So
feet.
you got 15 inches, you got 1 foot is 12 inches. Yeah, so make it a nice little fraction, right? What's that fraction?
6.
5/4.
5/4.
So it's 5/4 of a foot. Cool. Because 1/4 of a foot's 3. That's how much extra inches it has over a foot. Cool.
Yeah.
So that's 5/4 foot radius. And of course the mile we just figured out earlier was,
5,280.
yeah. Alright, so if it travels a mile, that means the wheel, so it starts at 0, that means the wheel will, the distance at this point is gone would be a mile. So how do you think you do this? If I traveled 15 force feet in my car, right? Okay, right. If I went 15 force feet, let me see, how do I say this? So what do I want to do that before I say, what do I have to figure out about the circle?
Circumference.
Circumference. So circumference would be 2 times pi times r. Pi over 2 feet. So then I really just, the question is how many of those circumferences fit into a mile? Exactly. I love it. So how do I do that? Divide. Yeah. So just take 5280 divided by that. You can make it into a decimal, obviously. Again, I don't want you to tell me, I live about 700 pi miles away. What the hell's that? Who are you? Okay, cool. Is that good? You guys? I love it. I need little clickers. If they would only work all the time, I'd get clickers so that I could actually. Then I'd have me somewhere out there because I would be the smart ass doing all the weird answers, throwing everything off. All right.
Oh, the like eye clicker things? Is that what you're talking
Yes, so I can get responses instead of these. Go to Full House. Oh, shit. All right. Is there anything else? One last question? Anything else? There's plenty. Yeah. Okay. Oh, cool. All right. So this is a true story. Greek mathematician, have fun with that name, measured the circumference of the earth from the following observations. Blah, blah, blah. So he noticed that on a certain day the sun shone directly down a deep well in Syene, modern Aswan, in case you wanted to know. At the same time in Alexandria, 500 miles north on the same meridian. So I can basically look at the earth as one big circle. That's what they're telling me. It's on the same meridian. I don't have to worry about 3 dimensions. Thank God. The rays of the sun shone at an angle of 7.2 degrees. So they give you the nice picture. So they're saying try to figure out the radius and circumference of the earth. So the basic setup is here the sun is shining directly down this well. So you can see the little girl. No. And here it's shining.
I gotta do it quick.
That took a turn. And here it's shining at 7 degrees to the 7.2. So using basic geometry, I need to, how am I going to figure out the circumference of the earth first? How would I do that?
By finding a radius.
Okay, good. And how would I find that radius?
You use theta times the arc length.
Because what else do I know
Theta
here?
equals
You know
The little thing I didn't really put down here is this distance is
500 miles.
500 miles. And that, of course, is the arc length. And, of course, S equals theta times r. So if I just knew what the hell this angle was, and, of course, we do know what it is. Very basic geometry. I don't know if you guys remember.
7.2.
7.2.
Well, that's not a good thing to admit right now. Right. So this would be...
Same.
7.2.
Yeah, simple. Because that's transversal through these parallel lines, right? Cool. So they're corresponding angles because they were made in the same way. Okay, so once you work that bad boy in there, you know that S is r theta, and then you just got to plug each other. So now you can figure out what the radius is in miles. Once you know the radius, you can answer the next 2 questions. All right, they ask you the radius, and then, that is the 2 questions, the radius and the circumference. Yeah, cool. Is that cool? When you first read through that, it's like, holy shit, I'm supposed to do what this Greek dude did? What the hell? But it is kind of cool when you read about how they first estimated the mass of the Earth and all this stuff, and there was just no way for them to possibly be able to do that easily. So you knew it was difficult. And it's really awesome to me. They're all like, we got nothing going on. There's no internet yet. Let's walk around the Earth and see what's going on. Yeah?
Before you plug it in to find out the radius, you have to convert the degrees into...
Totally, thank you. So to use this equation, the angle has to be always in radians. Cool. So now we're almost to the point where I can say this fully. Whenever theta is not sitting inside of a trig function, so if I said sine theta, if I said sine of 30 degrees, could anybody right now tell me what that is? Sine tells you what piece of the point? The y piece. So at 30 degrees, what's sine of 30? 1/2. You guys kick ass. So sine of 30 degrees is 1/2. That's the only place I could safely use degrees, is when it's inside a trig function. Because the sine doesn't do something to 30 degrees. The sine just says, oh, 30 degrees represents this. It represents how many radians is 30 degrees? 5 or 6. So it's not like taking a square root of something. Right? The sine of 30 degrees is the same thing as the sine of 5 or 6 radians. Yes, sir.
So sine 60 would be at 30.
Beautiful, because I'm getting closer to y, and y-axis is where sine is biggest, because sine likes y. Kick ass. Whenever you see an angle then sitting by itself, you definitely have to use real numbers for it, not degrees. So you have to convert that to radians.
And that's why you said that degrees are kind of not...
Are made up.
Yeah.
Exactly. So they work here because they mean the same angle as 5 or 6 does. And that's all sine cares about, is where the hell are you? So 30 degrees still tells it where it is. But out here, putting 30 degrees there doesn't make any damn sense. The math doesn't know what that means. The math needs a real number there, and that would be radians. Cool. Okay, maybe not. Somewhere in the middle there. All right. So that's it for the questions. I want to get into 6.2. We really barely got into 6.2. Blah 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 blah. Oh, okay.
Yes. No.
So let me go down that same thing we were just going down. These are the kind of questions, and I want you to realize this. Trig quizzes and tests will all have, will at least either be a part 1 and a part 2, where you can use a calculator on one and not the other, or there'll be entirely no calculator. Probably it'll be part 1, part 2. Because I want you to be able to do sine of 71.3, and you're not going to have that memorized, hopefully. So the very first thing I want to do is some of these little quick fire things. So if I said, what's the cosine of, what you got, John? Pi over 4.
1/2. Or no, root 2 over 3.
Alright, so let's do this. So for the rest of these, let's do it this way. That one I threw out to everybody. Let me write down some more. Don't say anything. Alright. So some of you guys might not be here yet. And right now it's perfectly fine to use the handout. But if you've attempted to start memorizing these things, maybe don't look at the handout. Try them out. See if you get them right. Quizzes and tests, you obviously will not be able to use a handout. You have to know those. that's the
Just making sure.
same, yeah, good. All right, guys, so we're pretty much in a you know it or you don't situation. So the last one, what do you have to do with the last one?
Use a reference point.
Good. So let's sign a pi over 3.
Right, 3 over 2.
Good, because pi over 3 is also 60 degrees. So rad 3 over 2. So again, let me just tell you, the way I do this, I don't have anything memorized. I just think, okay, pi over 360 is closer to 90, sine's biggest, root 3 over 2. 45 is where they agree, root 2 over 2. And then the smallest value out of the ones I have to memorize is 1/2, not 0, but 1/2. So that would be where sine would be 1/2 when it's close to the x-axis. That'd be pi over 6 or 30 degrees. And cosine would be 1/2, the smallest value, when it's close to the y-axis. Because cosine likes x, sine likes y. Yeah. Tangent of pi over 4.
1.
Yeah, why is it 1?
Because it's right 2 over 2, right 2 over 2.
Yeah, because it's sine over cosine, and sine and cosine at 45 degrees are the same. Cool. So here, what's your reference angle for this? Pi over 6. So on a quiz and a test, I will ask you to show me reference angle work, and then give me the answer. Right. So all you got to show me for reference angle work is this kind of thing. You got 5 pi over 6, so this would be pi over 6. So another way you can kind of do this, you can either just go directly, cosine of pi over 6 is, yeah, because it's closer to x-axis. So it's rad 3 over 2, but
It's negative.
it's negative. Or you can realize you could actually rewrite this as it's equal to negative cosine of pi over 6. And of course that's kind of like just writing down what we just did, right? But you could actually figure out the reference angle, and then you can figure out if it's negative or positive, and then you can just focus on this piece to see what that is. Just as long as one of those approaches makes sense.
Does it matter how we memorize them?
No, it never does.
So like if I think about it and just how many times it goes around closest to 1 or 2.
However you want to think about it.
Okay.
However you want to think about it. I like it. Okay, cool. Yes, sir.
So I'm just trying to understand how there's a negative in the... Oh, because it's on the...
Because back here, x is negative. Yeah, so all you got to do is memorize the first quadrant stuff, and then if it's cosine, cosine's going to be negative, second and third, because that's where x-axis stuff, that's where the x is negative.
Cosine's going to be...
Negative in the second and third quadrant.
Oh, we're talking about reference point. Isn't it always positive?
No. Cosine is negative in the second and third quadrant. Reference angles are always positive because they're distance, yeah.
Okay.
All right, so let's complete this list of trig functions here. So we got sine of an angle is y over r. Sometimes you'll see it over h, right, over the hypotenuse. So when we're looking at triangles. Cosine is what?
Y over X over R.
X over r. Tangent, y over x to cast. So here's the other ones we haven't talked about yet. And the way I remember this is S goes to C, C goes to S. What the hell I mean? So sine theta is this. Cosecant. Cosecant. C, no Jeff, you can make a C. C, S, C. The cosecant of an angle. It's the reciprocal of the sine. S goes to C. So if sine theta is y over r, cosecant must be r over y. So cosine theta, its reciprocal would be secant. S-E-C. That would be r over x, yes. And then the nice one is tangent and cotangent.
X over y.
Yeah, so the cotangent of an angle must be x over y. Okay. So I want to do a couple of triangle problems because that's where a lot of our early trig work is going to be really focused on triangles. And the unit circle is full of triangles, so it's really nothing new here, just a little more direct. So if I gave you a triangle, and I told you that this side is 4, and I told you this side is 7. What two trig functions could you tell me? Well, let's do it this way. Okay. We're just starting to talk about this. What do I have to do before I can find all 6 trig function values? What do I have to do?
Find out what the
Find
other
the,
side
what
is.
the-
Find the x side, right? I can't make cosine or secant unless I know this side. Or tangent, cotangent. So, how do I figure this out?
P squared plus B squared over
Yeah.
C squared.
So you get 7 squared equals 4 squared plus x squared. So x equals 49 minus 16,
33.
33, square root. Of course, you should realize most triangles that you just come up with are always going to have some root somewhere in them. It's very few. There's relatively fewer triangles that have nice whole number sides. 3, 4, 5, 5, 12, 13, so forth. So now this is exactly the kind of problem I'm going to give you. Exactly. And I'll say find the 6 trig function values of theta, or I might put an a there, or I might put something else there, who knows. So what would sine of theta be? Yeah, 4 over 7. Now real quick, the reason that the way I approach this works is because the angle is in the base. If I had asked for this angle, I would have just turned my triangle around. So I think after we do this problem, I'll show you SOHCAHTOA.
Ew.
And then you can, not suck a toe. Yeah.
Can you say that again about if you had to flip sides?
This only works. Y and x are defined to be what they are, the x-axis, the y-axis, if the angle is in the base. And think about it from what we did with this. We always talked about the angle being here, or there, or there, or there. So the angle would have to be in the base of the triangle. So if I asked about this angle,
Okay.
I'd have to actually turn the triangle. Yeah. I'm sorry, that was nothing. Thanks for the question.
So it has to be connected to basically the center of the circle.
I see what you mean, yeah, exactly. But for a free floating triangle, it's got to be in its base. So if it isn't, you just turn it. So what's cosine theta?
Rad 33 over 7.
Yeah, exactly. Rad 33 over 7. Does everybody see where those are coming from? Right now is a really good time to tell me if you don't. Michelle, you all right?
No.
You always have this look and you never say anything.
Oh, because it's R.
Sine is defined to be the ratio of what sides? These 6 trig functions, all trig functions are basically, and this doesn't sound like you do a lot with them, but you can do a shitload with these things beyond what the basic definition is. The basic definition is ratios of certain sides of a triangle. So sine, if I put the angle here in the base, can't be up there, but it has to be there, sine will always be the y side divided by the hypotenuse.
So R is going to be the hypotenuse.
Yeah, so that's what I said earlier. Sometimes you'll see this an H here instead of an R.
Okay.
But can you imagine I could
That's
draw
what I
a
was
unit circle and this would be the radius, wouldn't it?
Yeah.
Okay, good. So that's where I got 4 over 7 for sine. Cosine is x over r, the x side divided by the radius or the hypotenuse. How are we doing so far? What's up, you okay?
No, it's just the picture doesn't line up to me where 7 would be the radius. If that's supposed to be like,
So it would be not a unit circle, but a 7, right? So here's 7, here's 4, right? And here's through 33. Now here I'd have to specify it's negative.
okay.
But it's really just here, just turn around, or you're kind of with me. But I just wanted to put it, so I could put it here, and it's just turned around. And that's more of a related to what we got, because it's a positive root 33. Somebody just flipped the triangle.
Okay.
Do you guys see the connection? All right, good. I don't want to make a big deal out of this. I could have put an H there from the beginning, but everything we talked about up to this point involved radius of unit circle. But the hypotenuse, because remembering, any triangle I can fit in here. Any right triangle, let me be careful. Any right triangle I can fit in here, and its hypotenuse will have to be the radius if it's going to fit in its little circle. So that's why I can look at them as the same kind of thing. Good, you're good, yeah.
So because we're in quadrant 2, when we're writing cosine theta, would we include
No.
this
You gotta be
negative?
careful. A triangle just sitting here on its own does not have to always face this way if it's positive everywhere. It could be any damn way it wants to be, right?
But they need to be positive.
Yes.
Okay,
Unless we're told otherwise. But this, if I give you a picture of a triangle, they're definitely like 4 feet, 7 feet, so it's
Okay.
not going to be negative.
okay.
We'll get to a point where we can make our own triangles, and we can actually draw them very specifically because maybe one side is negative. So it's not a physical triangle, it's just a triangle from a unit circle, like a representation, right?
Right.
This triangle will be negative.
But we don't want to worry about it.
Not yet, I haven't told you what quadrant you're in. So if I say you're in quadrant 2,
Then you include it.
then a triangle I draw to help me would have a negative here.
And then you, if you.
That's in our future, yeah.
Okay.
So what's tangent?
4 over rad.
Yeah, it'll be y over x, or sine over cosine, 4 over rad 33. Now that's not good enough. What's wrong with that number? It's good. So that's going to be part of your world. Take a second and rationalize it. All right? So times rad 33 times rad 33, you get 4 rad 33 over 33. So just make that an automatic thing you do. If you end up with a radical on the bottom, you have to rationalize it. What about cosecant? Now all these guys are easy once you have the
7
first
over
3.
4. Just flip it.
Yeah, just flip it. So cosecant would be 7 over 4.
7 over.
Secant would be,
7 over rad.
yeah, shit.
3 over 33.
Yeah. So whenever you have a rad on the bottom, you just have to turn around. So this will be 7 over 4 because cosecant is 1 over sine. Secant is 1 over cosine, so that'll be 7 over rad 33, which is 7 rad 33 over 33, just the same way we did this one. Now when you go to do cotangent, what are you going to be smart about? Use the original exactly, because when you flip that guy around, he's cool.
Yeah.
Don't flip this dude around, then you're like double rationalizing. It's like, oh god. So this was 4 over rad 33, so the cotangent would be
33.
rad 33 over 4. I love it. So right now, and actually forever, of course, but right now, the 6 trig functions are just ratios of sides of right triangles. When you remember that in 3 years, wherever, how far you're going in math, when you think about that, you're like, all the shit I've done with trig functions, and there's a lot of shit you can do, and that's really all they are, just ratios of sides of right triangles. It's insane. Okay, cool. So, was there one more thing I wanted to say? No, it's good. Let me give you this so I can shut up. I've been talking way too much. Oh, that's right. That was the last thing I wanted to do. SOHCAHTOA. I don't like it, but what the hell? Some of you guys know it already?
I remember it.
Okay, there's SOHCAHTOA. So what the hell? Let me just label this in general. Let's make this what the hell's on? Jeff, you want to put one? Okay, sure. Right triangle. So sine of this, what would the sine of this be?
Opposite of the hypotenuse.
Alright, so those of you who know SOHCAHTOA, right? So it'd be y over r, but that's the opposite side over the hypotenuse, right? That's sine is opposite over hypotenuse. So you see how this works? Cosine would be adjacent, so cosine of theta would be x over r. That's the side next to my angle, the adjacent side over that hypotenuse. And of course, tangent would be opposite over adjacent. Now, if you don't like it, or if you've never seen that, and that's just confusing, awesome. Don't ever do the damn thing. You don't need it. The only thing this has any sort of advantage about is if I draw a triangle and I put the angle, Jeff, you can draw a right triangle. I don't know. I put the angle there. I'd have to just take a second and either flip it or do the remarkable difficult thing of just doing this. The SOHCAHTOA would be, if I want to know, so this is like 3, 4, 5. If I wanted the sine of theta, I'd have to do this and realize that's the y, so it'd be 3/5. SOHCAHTOA would say opposite over hypotenuse. Right, so you saved a full 0.3 milliseconds there. I mean, so it's really, that's the advantage of SOHCAHTOA. If you like SOHCAHTOA, you've learned SOHCAHTOA, use it. I want you to realize you're going much further in math. It's only going to be helpful for a little bit. It's much, I desperately want to understand, if you know cosine likes x, you know sine likes y, future things you learn that build on that will make so much more sense. That's the only reason that I don't like this. Same thing with FOIL. FOIL only takes you so far. Okay, so here, either way you want to do this, either SOHCAHTOA if you know it, or the much better way of this. Sorry. Yes?
What happens if you have like, kind of, I don't know if you're good, this, like, say it says the secant of negative, in parentheses, negative pi over 6. What the hell does that mean?
Oh, so then you have to figure out reference angle.
Yeah,
Which quadrant are you in?
okay.
Yep.
So just going the opposite direction.
So secant, if I see secant, what do I really think about? I really think
Why?
cosine. So I get the answer for cosine,
Yeah.
and if I'm negative pi over 6, which quadrant am I in? Fourth. Does it go back? Reference angle is obviously pi over 6, because that's how I got there. So if you figure out what cosine of pi over 6 is, secant would just be flipping that dude over.
Less.
Thank you.
I stole this from some worksheet I found online, so I only stole a few of their triangles. That's why there's number 1, 2, 3, and 7.
Okay.
Aw. Are we turning this back in, or is this just?
No, this is just for you guys. We're going to talk about it. I should have brought that too. Yeah.